So exponential functions, an exponential function is a function of the form f of x is equal to b to the x. And we'll actually expand this. We consider all of the function operations, all of the shifts, translations, stretches, reflections, all of the transformations of functions. We also can apply to these and still consider them exponential functions. So we'll also consider most commonly, I would say, we see a constant out front. So I can denote it by a times b to the x. Sometimes we have a c times b to the x. Sometimes like a p or a p naught times b to the x. When we talk about population growth, exponential functions are going to come up. Radioactive decay, exponential functions come up. So sometimes there's just this a corresponds to our initial amount, oftentimes. And then as well, if we apply other translations, like add constants either in the exponent or outside to shift left and right, up or down, all the transformations we know. But for now, while we're introducing the function, our root function, our base function, is just b to the x, where b is a positive constant that is not equal to 1. We don't like having the b term equal to 1 because 1 to any power is just 1. And we call this b the base of the exponential. So base 1 doesn't even make sense because 1 to any power is always 1. And we also don't allow negative numbers, because if I have negative numbers that I'm now raising to exponents, things can get a little weird, especially if those exponents correspond to, say, a square root. We don't like square roots of negative numbers. So we just restrict our base, excuse me, to 0 to infinity. I just swallowed wrong again. Excuse me. So what are the key features of our exponential functions? Just like with our polynomials, rational functions, lines, we kind of want a method for graphing these. Graphing these is a way we can visualize it and then get information about the behavior of the graph. I'm not going to list out steps or anything, just because hopefully the steps we've seen from the previous graphing techniques, rational functions are probably the hardest ones to graph. So hopefully you guys can kind of create your own steps if you want. I'm just going to go ahead and list the key features, and then however you apply those, whatever order you want to apply these into graphing, hopefully you'll be able to figure that out on your own, whichever method works for you. But typically, of course, we want to start with easy things like points, in particular the intercepts. So f of 0 equals 1, meaning that the y-intercept is 1. Always passes through 1 on the y-axis, as long as I have this constant term. So this, we can call this like the lead coefficient or the constant coefficient or the constant multiple. If this a is just 1, we essentially just have b to the x. Always makes the y-intercept 1. In general, the y-intercept, if I plug in 0 for x here, y-intercept is going to be whatever that a value is. Then the other key feature is that we have a horizontal asymptote, y equals 0. So the x-axis. That's basically it for the things we can plot, right? Just like rational functions, we are looking for easy points, the intercepts and y-intercepts, x-intercepts and y-intercepts, and then asymptotes, vertical asymptotes or horizontal asymptotes. So for exponential functions, no x-intercepts, and then, of course, no vertical asymptotes either. Since our horizontal asymptote is the x-axis, we actually never cross it. It always just approaches the x-axis. So no x-intercepts on that guy. The domain and range. So our domains, remember, are determined by really throwing out numbers that will give us an improper mathematical operation. But here I'm just exponentiating. I'm putting my x's into an exponential, and I can have any exponent. So it doesn't matter. It's not going to give us a division by 0, not going to give us a weird square root of a negative number, as long as the base is positive. So our domain has no restrictions. Domain is all real numbers. The range is 0 to infinity. And then the last thing we'll note is we can actually get some information based on the base. So if most commonly we like it when the base is bigger than 1. Because if the base is a fraction, we can actually do some manipulations to make it an integer, or at least a number bigger than 1. In this case, it's going to be increasing. If the base is a fraction, less than 1, then it'll be decreasing. And then I just wanted to write down one note just on all of the arithmetic skills that are going to start coming up when we start manipulating and calculating and solving these exponential functions and equations. Negative exponents means reciprocal. Or sometimes we call it the inverse, multiplicative inverse specifically. Fractional exponents mean roots. So an exponent, right? Something raised to the 1/2 is a square root. Something raised to the 1/3, cube root. Excuse me one second. And since our domain for our x variables is all real numbers, right? I can put in anything. I can put in negative numbers. I can put in negative fractions. I can put in fractions, all in the exponent. So you just have to be very careful with understanding, remembering what happens when I have those kind of numbers in the exponent. What do they mean? As well as making sure you're keeping it straight if the base is a weird number as well, right? Our base, it's positive, but it could still be a fraction. So just make sure you're keeping that straight. If the base is a fraction, it's all right. When the numerator, or excuse me, when the exponent is a fraction, it corresponds to a square root. So let's go ahead and go over some basic calculations. Let's say we have f of x is equal to 9 to the x. And let's try to arrive at some of those key features that we were just writing down. The y-intercept, pretty easy. F to the 0, or f of 0, just going to be 9 to the 0. And any number to the 0 is just going to be 1. So y-intercept, always 1. Let's go ahead and compute some things. I can check f of 2. Well, that's just 9 squared. It's 81. So as we can kind of see, these numbers they get really big really fast when my base is bigger than 1. Even at 2, we're all the way up at 81. We can do things like f of 3 halves. And now I have 9 to the 3 halves. This is a fractional exponent. How do we deal with fractional exponents? I always recommend dealing with the denominator first, dealing with the root first, because that'll make things smaller. So I always, if we were writing out the steps, I write it 9 to the 1/2 cubed is what this means. And now 9 to the 1/2 is square root of 9. That gives us 3. We still need to cube it. And 3 cubed gives us 27. So you could do those in the opposite order. I could do 9 cubed and then square root. I would not recommend doing 9 cubed, though. I don't even know what that is, because we'd be 81 times 9. So much more mental gymnastics if you do it that way. And lastly, let's go ahead and do f of negative 1/2. So now I have a negative exponent and a fractional exponent. So 9 to the minus 1/2. With negative exponents, I always do the negative part first. So negative means reciprocal. So we want 1 over now 9 to the positive 1/2. So we essentially just take the reciprocal of the quantity and then change the sign on the exponent. I guess if we wanted to write this out a little more rigorously, we could do it like we did in the last step, or the last computation. 9 to the negative 1/2 is just 9 to the 1/2 all to the minus 1. And so if I have something to the minus 1, it just means 1 divided by that. So 1 divided by 9 to the 1/2. And now we can do 9 to the 1/2 with square root of 9. So we'll get 1 over 3. Graphing this, it's hard to get graphs of exponential functions because of how fast they grow. So what I'm going to do, let's see, let's at least get 9. I'm going to make the x-axis, the x scale, quite a bit bigger than the y scale. And let's plot the points we found. So y-intercept is 0. If x is equal to 1, we didn't compute that, but it's just going to be 9 to the 1. 2, 3, 4, 5, 6, 7, 8, 9. Cool. Just double checking my counting on those tick marks. So we've got the point 19. And let's see, any of these other points that we can plot, even 2, we're not going to be able to plot. It's all the way up at 81. We don't have room for that. 3 halves is even up at 27. So here we would be at 27. It's going to be even still too difficult to plot. We can plot the fraction one though. So negative 1/2. And of course, so even if it grows rapidly on one side, it's going to decay rapidly on the other side. At 1/2, we are down at 1/3. So really close to the x-axis already. And you can imagine now, 9 to the smaller fractions that I start to put in, or if I put in a lot of negative numbers, it's just going to give me a smaller fraction. And so we have this horizontal asymptote. And exponential functions never cross their horizontal asymptote. So it's going to be really small, really close to 0. And then it's going to shoot up really fast. and look like that. Let's do one more, and let's do one with a fractional base. So let's say we have f of x is 1/2 to the x. So we mentioned if the base is bigger than 1, it's increasing. And we can see how it's not only increasing, but the concavity, the curvature, it's curving upward. So we call this concave up, which means essentially that it's increasing the rate in which it's increasing. So not only is it increasing, but it's also getting steeper and steeper. So it's going to start increasing very rapidly. The converse is true when the base is a fraction. It's going to decrease, still be concave up. So it'll be decreasing, but sort of slowing the rate at which it's decreasing as well. Let's plot some points. Even if the base is 1/2, when I plug in 0, we'll have 1/2 to the 0 is still 1. And so why should this be decreasing? Well, let's plot some more points. What's going to happen if I plug in 1? It'll be 1/2 to the 1. Which gives me 1/2. And if I plug in f of -1, well, now we have 1/2 all raised to the -1. Something to the -1 means reciprocal. So it's going to be 2 over 1, or just 2. And for the sake, let's do one more. Let's say f of -2. So we will have 1/2 to the -2 is the same thing as taking the reciprocal. So 2 to the positive exponent, and 2 squared gives us 4. And so plotting this, still going to keep my x scale a bit broader than the y scale. We've got our y-intercept, 0, 1. We've got 1, 1/2. So about right there. -1, we had 2. And -2, we were up at 4. And now we're going to see what's going to happen as x gets bigger and bigger. It'll just be 1/2 to a higher power. So I'm just taking 1/2 and multiplying it more times by itself. Every time I multiply 1/2 by itself another time, it's just going to get smaller and smaller. So we're going to decay. We're going to approach 0, but we'll never cross it. So we've got this horizontal asymptote still on the x-axis. And now our graph is going to look something like this. And so this is our f of x is 1/2 to the x. And so the last thing I wanted to talk about with these guys, well, let's try to figure out, well, why some other ways to think about this f of x to the 1/2 x. I kind of was mentioning what happens when we have these fractional bases. Sometimes, for me personally, I don't like dealing with fractional bases. I would rather write it as a whole number. Unless we're doing exponential decay, sometimes like half-life formulas are really nice to just write as a 1/2 base or a fractional base. But if you look at it, this graph, it just looks like taking a graph with a base larger than 1 and flipping it across the x-axis, or excuse me, across the y-axis, flipping it horizontally. And so what you can think about is when I have these fractional bases, you can play around with these negative exponent concepts. So let's say we have our f of x still as 1/2 raised to the x, and we want to compare it with g of x, which is just 2 to the x. Well, whenever we have multiplication or division to an exponent, exponents distribute over multiplication and division, not addition or subtraction. Be careful with that. So I can write this as 1 to the x divided by 2 to the x. But 1 to the x is just 1. So really it's 1 divided by 2 to the x, which we can actually write as 2 to the negative x if we want to use these negative exponents. And when we have a negative inside the exponent for exponential functions, this actually corresponds to a horizontal flip. This is just g of minus x, right? If I plug in a minus x for x into this function, we get exactly that. So in other words, we can obtain the graph of f of x by taking our graph of 2 to the x, which would have been a typically increasing exponential function, and then flip it horizontally, do these horizontal adjustments. Any questions on that?